This presentation is brought to you by the Transportation Learning Network. TLN is a program at the Upper Great Plains Transportation Institute at North Dakota State University. We are a dynamic partnership with the 4 state DOTs of North Dakota, South Dakota, Montana, and Wyoming, along with the Center for Transformative Infrastructure Preservation and Sustainability, also known as CTIPS. Through these partnerships, TLN delivers tech transfer, best practices, training, and research to the transportation industry. For more information, visit our website at translearning.org. Research materials can be accessed through the CTIPS website, and I'll place that link in the chat once I'm done here. A recording of today's session will be available both on YouTube and the CTIPS website after the session concludes. Please give us a couple days to get that processed and posted. To help maintain a smooth experience for all participants, please set your status to Do Not Disturb and ensure your microphone is muted when not speaking or asking a question. If you decide to take a call, please make sure you are muted on the call here so you don't interrupt our presentation. Feel free to ask questions or request clarification at any time throughout the presentation, and we will address those as they come in. Our speaker today is Biao Quang. He is a graduate research assistant and PhD student in the Department of Civil and Environmental Engineering at the University of Utah. His research focuses on artificial intelligence, computer vision, and machine learning applied to civil infrastructure, disaster resilience, and asset management. With that, Biao, I'll go ahead and mute myself and let you take over from here.
Okay, great. Thank you so much for the introduction, Chris. Appreciate that. I will start my presentation. Okay, good morning, everyone. Thanks for attending the project seminars. I'm Biao Quang. I'm a PhD candidate at the University of Utah. Today, I will present our CTIPS funded project on artificial intelligence and mobile phone-based transportation asset inspection. The project number is CTIPS 0007. This project focuses on two major roadway maintenance issues: pavement marking, condition assessment, and litter identification. Pavement markings are critical transportation assets because they provide roadway guidance, warnings, and non-information for drivers and pedestrians. However, pavement markings are easy to deteriorate due to traffic wear, weather exposure and slow for operation. As shown in these examples, many markings become faded and difficult to recognize. These deteriorated markings can reduce visibility and increase safety concerns. Therefore, pavement markings require frequent inspection and timely maintenance. In addition to pavement marking deterioration, another important roadway maintenance challenge is roadside litter and debris. Examples including like the vehicle debris, plastics, leaves, and roadside waste. These materials not only affect roadway cleanliness, but also obstruct drain systems and roadway operations, and introduce traffic risks. According to the previous reports, roadway debris contribute to over 50,000 crashes in the United States between 2011 to 2014. As a result, transportation agencies require frequent roadway inspections to identify and remove these issues efficiently. However, inspecting transportation assets at large scale remains difficult using traditional approaches. Therefore, a scalable and automated inspection workflow is urgently needed. Currently, roadway inspections rely on manual efforts or specialized inspection equipment. Manual inspection processes are often labor-intensive, time-consuming, and subjective. Specialized in inspection devices, for example, the retrorefractometer can provide accurate measurement, but they are expensive and difficult to apply on a large scale. As a result, traditional inspection approaches are not ideal for a large scale and frequent roadway inspection. This creates a strong lead for more automated and cost-effective inspection solutions. One promising solution is the application of artificial intelligence. Recent advances in AI have significantly improved automated transportation asset inspections. AI models can automatically detect and classify roadway issues directly from images or videos with high accuracy and near real-time inspection. Previously, studies have successfully applied AI to pavement distress detection, traffic sign identification, and pavement marking evaluation. Our previously MPC-funded project successfully demonstrates the capability of AI in detecting objectives using mobile phone-based video data. The press work focuses on object identification. It aims to answer the question, what's the object? For example, our previous framework could identify whether the object is faded pavement marking or roadside litter, just like these two screenshots. However, practical transportation asset management requires more than simply identify the roadway issues. Transportation agencies also need to know how many issues exist within roadway sections and where are the objects located. They are also interested in how can this result be visualized or interpreted. Therefore, important gaps remain in this field. To address these gaps, this study develops a comprehensive AI-based transportation asset inspection framework. In this project, we aim to extend our previous work by developing a more comprehensive and scalable roadway inspection framework. Specifically, this study focuses on 5 major objectives. First, expanding transportation asset datasets. Second, improving object detection performance. Third, developing object counting capability. Fourth, estimating geolocation of identified objects. And finally, building an interactive visualization interface for transportation asset management. These five major objectives can bridge the gaps in our previously framework. This slide presents the overall workflows of developed framework. First, we use a mobile phone to collect the videos and the GPS data. The collected videos are converted into images and manually labeled for AI model training. Next, we use Euro detection models. We use Euro to train the detection models to identify pavement marking issues and roadside litter separately. Then, based tracking algorithms are used for counting unique roadway issues. Afterwards, GPS data and interpolation methods are used to estimate the geolocation of identified objects. Finally, the outputs, including the cropped image object class, inspection information, and the geolocation of this identified object, are integrated into an interactive visualization interface. Overall, this framework combines detection, counting, geolocation, and visualization in a unified transportation asset inspection workflow. First, for data collection. In this project, a mobile phone was mounted on the inside windshield of a car to record forward-facing roadway videos. At the same time, GPS data are also collected using a mobile phone-based GPS tracker. The videos are recorded across highway and local streets in Utah. Different lighting and weather conditions are also considered to improve model robustness. After collecting this data images, we use of spatial tools to label these images for pavement marking and litter separately. For pavement marking issues, we developed a dataset including around 7,000 label images. The pavement marking are classified into two categories in our project: white faded markings and yellow faded markings. White faded markings include all line markings, arrow markings, and water markings in white, just like these pictures. Yellow markings are the faded double and single curve or line markings in yellow. For roadside detection, we developed another large data set. Roadside litter or trash is classified into four categories: white litter, black litter, dirt, and leaves. White litters are the litter in white or bright colors on the roadside. Black litters are the litter in black color or dark color, including the tire debris, rubber or branches on the roadside. The dirt are we also consider the dirt along the concrete guardrails and the leaves on our local street, but we also can find some leaves on the highway. For detection tasks, this study roadway 8 as a key object detection architecture. Euro is a single-stage object detection framework that performs localization and classification at the same time. Therefore, this model has high computational efficiency and can be used for near real-time roadway inspection. Using this labeled dataset, we trained separate models for pavement marking issues and roadside litter detection. This slide presents the metrics to evaluate the performance of the trained detection models. We select the precision rate to evaluate the reliability in classifying objects as positive, and the recall rate to assess model's capability to detect positive objects. We also select the F1 scores to evaluate their performance as well. For pavement marking issues, the model achieved strong detection performance with an average precision scores of 0.88, recall rate of 0.89, and F1 scores of 0.88. It's a good performance. Here's a short demo videos which shows how detection models identify pavement marking issues on I-250 highways in Utah. You can see this demo videos. It can detect the faded white markings on the highway. In the short demo videos, we can see almost all faded pavement markings have been detected. And then from this example images, we can see the models successfully identify different types of faded pavement markings, including the line markings and the word markings in white, the arrow marking, and some faded yellow marking, single or double line yellow markings. Our model also has decent performance in detecting roadway litter and trash. It achieves an average precision of 0.86, recall rate of 0.82, and F1 scores of 0.84. Let's watch this demo videos regarding identify different categories of litter and trashes on the roadways. It can identify the dirt, black litters, and some white litters on the highways. and also some black litters. That's the debris on the roadside. So we have the performance on detecting the litter on the roadway is also good. Here's some examples. We can see some black litters on the highways. The white litters on the highways have been detected, and the litter on the street road and some dirt close the concrete guardrails has been identified as well. Object detection alone is insufficient, as we just said. Object detection alone is insufficient for transportation asset management. In the last two demo videos, we can see the same object appears in multiple frames, which causes overcounting. Here's the detection result of the videos. We can see this frame from frames 44 to frames 48 should be the same object but has been detected in multiple times, which is overcounting. The same for the litter and trash on the roadways. This object are the same object but also has been detected in multiple times. As we know in practice, counting is very helpful for maintenance planning. It's better to know how many detected objects, radius or road sections, so that the transport agencies can planning their fixed work. So this study adopts batch track as a key object tracking algorithms. By applying batch track, objects are assigned unique IDs in a sequence of video frames by analyzing the spatial similarities and appearance similarities. The tracking links detected objects across frames. In this way, the counting models reduce duplicate detection and allows reliable counting of unique roadway issues. Next, I will present a case study showing the counting results. This case study was conducted using around 35 minutes of highway video data collected in Utah. In this case study, we will show how the pavement marking issues and litter are counted along with the detections. First is the demo videos to show how we count pavement marking issues. And please pay attention to the green words on the top left. We can see when the object is detected, the count number will increase as well. Finally, in this case studies, around 35 minutes videos, there are 580 white faded markings in the test road sections. Then in this demo videos, we'll show the result of counting identified litter and trash on the roadways. We can see the count number increase when the object is detected. Some dirt has been counted. Black litter. Black litter as well. So in this test road sections, there are 33 white litter, 263 black litter, and around 100 dirt on this test road section. After counting roadway issues, the next step for us is to answer or determine where these issues are located. Accurate geolocation is essential for practical maintenance planning. Transport agencies not only need to identify roadway issues, but they also need to know their locations to prioritize the maintenance work. In this section, we aim to answer the questions: Where are these detected objects? Let's first review what we have done so far. We have used our mobile phone to collect videos, which are 30 frames per second. Based on the detection and counting models, we can obtain the timestamps of each detected object. Meanwhile, we use a phone-based GPS tracker to record GPS information. It records 2 times per second. The timestamp of GPS record can also be obtained. We can see the times of GPS record doesn't match the timestamp of detected object. Therefore, detected object is not able to fully match it with GPS record. Here we propose a time-based interpolation method to estimate the latitude and the longitude of the object. In this way, the geolocation of the detected object can be estimated. To evaluate the geolocation performance, we conducted validation using around 3,500 GPS records. Among these records, 175 record points are randomly selected as ground truth. Then we use remaining points. The remaining points are used to estimate this point. Next, we compare the estimated location with their ground truth. Finally, it achieves an average distance error of only 0.27 meters, which is the performance of the geolocation estimation is good. Based on the proposed framework, we have located the identified object in the case studies for faded pavement markings and litter or trash. Each identified object is marked using a marker. We can click each marker. We will see some inspection details, which are the visualization interface we proposed. For example, for the pavement marking, if we click this marker, we will see a pop-up windows. The pop-up windows include many details of the identified pavement markings, such as the geolocation, each including the latitude and the longitude we just estimated, the class of the object, which is white faded markings. We're also including some inspection information, such as the inspection time and the driving speed at that moment we inspect these areas. It also includes crop images of the object to show how the faded marking looks like. The same for litter and trash detections. We also applied these visualization platforms to demonstrate each identified litter or trash. We're also including the geolocation and inspection information of these identified litters and crop images of these black litters to show how the black litter looks like, so that the transportation agencies can fix or remove this litter. This visualization is very helpful for planning maintenance work. It can be used to map pavement marking issues, visualize litter distribution, based on which, as we just said, transportation agencies can identify maintenance hotspot areas to plan fixed work. To summarize, this project has extended our previous work by developing an end-to-end AI inspection workflow. It included object detection, counting, geolocation, and visualization. Object detection can detect different objects, such as pavement marking issues, with 2 different categories, litter and trash in 4 categories. We have developed the object counting capabilities to quantify the number of identified objects within a road section or just a video clip. Third, we have improved the capabilities to geolocate the identified object to estimate the location of each identified object. We have proposed a visualization interface to represent the details of each identified object on an interactive map, which including the geolocation, object class, inspection information, and the crop image of the identified object. For the practical contribution of this project, this study developed an integrated AI-based transportation assets inspection framework. This is a low cost. We only use the phone to collect the data and deploy it approach. It supports proactive and predictive inspection and maintenance. It improves the roadway cleanliness and safety. It also bridges the AI and the infrastructure management. This project also contributes to research and deployment implementation. Based on this project, we have one journal paper just get accepted by Journal of Computing and Civil Engineering, and also published it. We also have published our conference papers. Besides this project also has some practical implementation. Utah has expressed strong interest in the developed AI inspection framework and its application in transportation asset management. The developed framework allows low-cost, scalable, and frequent inspection of transportation assets. That's all. Do you have any questions for this project?
I do. So great information. I like it. So a couple of questions, and I'm not sure if I missed it. So I do see here you're collaborating with Utah DOT
Yes.
to provide some of this information. So is this when this is done? Is this being are there certain criteria that are being used to flag the maintenance forces or a point of contact with Utah DOT to say if it's a large piece of debris, is it being flagged through the data through either some criteria that you set that if it's over a certain size or if it's if it's in the traveled pathway,
Yes.
is there something that will then notify the authorities to say, hey, we've got an object in the road that needs to be addressed sooner than later? Is there any kind of communication back and forth with that?
Thank you so much for these questions. Actually, we have communicated with UDOT with this project, and also have some another contact with UDOT in the same topics. Actually, this project has been directly applied to current UDOT practice, but they say, okay, this idea or this practice is very useful. They have the interest to apply it in their future practice. As you just said, it's very, very useful, such as to identify some big size trash or debris on the driveways, and the UDOT can clean this litters as soon as possible. I think that's very useful. But countries only express the interest to apply this idea to their future implementation.
Okay. Paul, you have a question? Go ahead.
Yeah, I have a question. Please, can you hear me?
Yes.
Yeah, I can hear you, Paul.
Yeah, so I see that you are using the GPS data from the GPS tracker
Yes.
to project the detected road markings, that is the faded and unfaded onto the map. But
Yes.
then this GPS actually gives the position of the phone and not the detected object. So how did you account for the offset, right, between the camera and the detected object without doing any spatial error or positional distribution? I don't know if you get the question I'm trying to say, because the GPS gives the position of the device and not the object. So all what you are plotting on the map using the folio is actually the position of the phone it's detected from the object, right? So how did you, incorporate, or how did you get that distance? Yeah, estimate that distance between the object and then the device because I didn't see any depth estimation between the detected object and the mobile phone. Yeah, that's my question.
Oh, okay. Thanks for questions. I think for this, we have collected the GPS information with the videos. So the GPS have the time, right? For example, this timestamps have this timestamp, and the videos we have the time of the videos like this the start recording times, like the start recording times. According to the start recording times and the frame numbers, we can estimate what time of, for example, for this one, this is the frame. This is an object that we detected its litter or its faded markings. We can base on these frame numbers and the start recording time of the videos to estimate what time of this identified object is. For example, is this time. So based on the time of this identified object and the time of these GPS trackers, we can match the two timestamps. So that we proposed the time-based interpolations to estimate the latitude and the longitude. This is time-based. We can obtain the time of the timestamps of the videos or the frames. We can obtain the timestamps of the GPS based on the two timestamps. We can estimate this geolocation. I hope I have answered this question.
Yeah.
Do you have any questions?
Thanks for that question. And I would also add, just for accuracy state purposes, I think the general vicinity would be in this case close enough for that estimated, because more than likely, with this, like you said, this test corridor that you went through, that I'm guessing as long as it's within 100 feet, really truly, the maintenance forces or whoever's going to go out for emergency response, if it's a tire in the middle of the road, you're going to be able to say, hey, it's within this this mile marker, and they're going to be able to find that relatively simple enough. So hopefully that. I did have another question, and that was, is any of this information, is it intended then to feed some of the navigation software, Waze, Google Maps, if it's Apple Maps? I don't know if that's the right word. I'm not an Apple guy. But is it feeding into the live data? So as commuters are driving on the road, and if they're using Waze or they're using some sort of mapping service, does it flag that as the object or debris in the roadway?
Oh, that's a really good and interesting idea. I think these ideas can be like the extend our this framework to apply in the future. For example, like if we drive in, we find out some things we can report in our map. That may be a potential ways that we can apply in the future.
Okay.
That's a really good idea.
And there's a question in the chat, and it says, what is the country of origin for deep system software?
I'm sorry, where's the question? Could you repeat these questions one more time?
Yes. What is the country origin for deep systems software?
Origins of deep systems. We only use the Euro as the deep learning architectures. What's the origins of? Do you mean
where is deep systems based out of?
Based out of
I may have missed that in the presentation, but the software that you're using for a lot of this data and the analysis of the data, was it called Deep Systems? Is that maybe where it was coming from?
It's not the deep systems. We haven't using any softwares to to train the models or apply any software to count or the geolocate this model. We only use these euros to train the detection models.
Okay.
So, yeah, we only use
Okay.
this euro to train these models. And for the counting and the geolocations, we develop our own algorithms to achieve the goals.
Okay.
Yeah. Do you have any questions?
Does anybody else have any additional questions that they'd like to ask at this point?
Oh, what?
Chris, I will go with one if we have time.
Yes, we do.
Okay, a nice presentation, Gao. I just want to ask about if you want to go on your precision recall and F1 score for the either the liter or the pavement markings. So is there any specific acceptable threshold values for those that has been guided from UDOT, or I mean, how do you decide like what's the right balance for all three matrices? Sorry.
Could you say that questions one more time? Sorry, I missed the
No,
final.
that's fine. So does UDOT tell you that what is a good precision value or recall value or F1 score, or is there any general guideline?
Do you mean for this metrics, for the performance standard, or the classification?
I can go with the pavement markings.
Okay. For this one?
Yes.
Uh-huh.
So you have shown some precision value, recall value, and F1 score. I think it's on the next.
Yes. Here.
Right. Just one slide
Here.
back. Yeah, this one.
Yeah.
So does UDOT gives any threshold that okay, 0.86 is a good precision score, or is it like 0.95 something you have to reach?
Oh, actually, UDOT hasn't given me a specific threshold to say, oh, you have to achieve that. No, actually, they didn't provide such information for us. But we see this matrix, I think is reasonable. I think it's also good if we compare the result with some similar studies. We can see the result we achieved right now is good.
Okay. And is there any balance should be there between these three different types of matrices? Like, let's say if the precision is 0.86, recall has to be at least 0.86 or more than that or less than that?
No, actually don't.
Okay.
Yeah, thanks.
I think definitely some criteria that could be implemented as states kind of start implementing maybe some of this this technology. So good question. Thank you. Paul, you have your hand up again?
Yeah, yeah, I do. From what I'm seeing from his presentation, I just wanted to be sure. So the mobile device was used to just collect the data, and then the detection and counting was done on a PC, right?
Yes.
Okay. So it is not in real time. It's been post-processed on the PC with a GPU, right?
Actually, thank you so much for this question, Paul. That's a really good one. Actually, right now, all the videos or all the results you see is post-processed. But I think they have the capabilities to apply it in real time. For example, if we connect our PC with our the camera or phones, when driving, it can detect the videos in real time. So it has the capabilities to achieve real time detection.
Yeah. So I mean, let me reframe the question. I was asking because with mobile phones, they have low computational power as compared to computers with GPUs. So when using, mobile phones, there's going to be some sort of latency. It's going to lag. So when doing the detections, it's going to lag. So I just wanted to be sure if it was a mobile phone that was used when showing the video, or it was post-process, but you've made mention that it was post-process. Yeah, I think my question is answered. Thank you.
Yeah, it has the capabilities, but country we cannot we can achieve that, but we didn't. Thank you so much for your questions. And I see one more question on the charging box information that is being collected about our research chargers, so it's easy to click from. Actually, this is for the data securities. We have this data hasn't been shared with anyone. Only stories in our research labs. Thank you so much for this question, James. Do you have any questions?
Are there any additional questions?
Or comments?
Good job, yeah. I really it was good information, and I think there's of course the crowdsourcing opportunities that are out there, but you just kind of wonder what's happening with the crowdsourced data. So I think it's really neat to have this as a kind of as an additional inspection tool and identification tool. I think it's really neat. So thank you guys for joining us today and being present in the moment. We truly appreciate your time, participation, and attention. We hope that you found today's session valuable and are walking away with some additional knowledge or insights. Be sure to bookmark translearning.org or even going to the CTIPS website. With that, thank you again, Biao. Certainly appreciate you sharing this information with us, and congratulations on the research. Have a fantastic rest of your week. Stay safe, and don't forget to be awesome. Thanks, everyone.